Good morning, students. In the last class, we studied what is energy and how we measure energy, how many types of energies are there. I told in the last class we are going to focus on mechanical energy, and we discussed that mechanical energy is available in two forms, that is kinetic energy and potential energy. Now today we are going to focus on kinetic energy. We will see what is kinetic energy and how we derive expression for kinetic energy. What are the examples of kinetic energy? These things we will discuss one by one. Now when you see the definition of kinetic energy, we know it is the mechanical energy, and how we define that we will see. Before that, I would like to ask one simple question. Have you ever thrown a stone against a glass window? What happens if you do so? As stone hits the glass, it breaks into pieces. Why does the glass break into pieces? What is the answer for this question? We know that when stone hits the glass breaks into pieces, right? When we throw the stone, it sets into motion, acquiring some velocity. As a result, some energy is stored by that moving stone. That means some energy is stored in the moving stone, and that's why it is able to do work of breaking glass into pieces. And what is that energy? The energy results in breaking the window when stone strikes it is the kinetic energy. And this energy, how that stone got? This energy stone got because of its motion. So the body possesses energy as a result of motion, and that energy we call it as kinetic energy. If anybody asks how we will define kinetic energy, kinetic energy is the energy possessed by the body by virtue of its motion, right? What is the definition? Kinetic energy is the energy possessed by an object by virtue of its motion. Without motion, no body gets kinetic energy. Now we'll see what are the examples of kinetic energy in our day-to-day life. Here you have to see vehicles are moving on the road, right? Vehicles, all moving vehicles possess kinetic energy. As they are in motion, they possess kinetic energy. So we can say all moving vehicles are having kinetic energy. Now we will see some more examples. Here you are able to see a spinning wheel. Spinning wheel, as it is in motion, no doubt it is not in straight line motion, it is in rotatory motion, right? But still it is in motion. That's why it is also having kinetic energy. We'll say that is rotational kinetic energy. Now we can see some examples in this. Here one train is moving, right? And this moving train is having a kinetic energy. You are able to see water is flowing in the river, right? This water flowing in the river is also having kinetic energy, right? So moving train is having kinetic energy, water flowing in a river is also having kinetic energy. Now we'll see how we derive expression for kinetic energy. What is the mathematical expression we use to calculate kinetic energy? On that we will focus now. Here we know that body is getting kinetic energy because of its motion. Now we'll try to derive the expression for kinetic energy, mathematical equation for kinetic energy. For that, consider a body of mass m which is initially at rest, right? Initially at rest means its initial velocity is 0. Now on that body, let us assume that we applied certain amount of force. When we apply force, definitely that body moves, that body gets displacement, that body gets velocity. Let us assume after applying force, it traveled s distance in the direction of force and got final velocity v. So like this, when I apply F amount of force on the body and after S displacement in the direction of force, it got final velocity v. Before applying force it was at rest, but now it is having some velocity. And when you observe this carefully, here force is applied and body also got a displacement in the direction of force. We say that positive work is done by that force. Why? Because force and displacement are in same direction, right? And this work done on the body itself converted into energy, and because of that it is moving, right? That means this energy in motion, we are calling it as kinetic energy, right? So to get kinetic energy, we did work on the body, right? Now we will see how we can measure the kinetic energy. So this kinetic energy is the amount of work done by the force to acquire that velocity. So we can write kinetic energy is equal to work done. I told it is a positive work is done. We know positive work is the product of force and displacement. Therefore, directly we can write force F into displacement S. But we know that initially, before applying force, it was at rest, but after applying force, it got final velocity v. That means you are observing the change in the velocity, right? That means there is an acceleration. We know Newton's second law. According to Newton's second law, force is always equal to the product of mass and acceleration. That's why F place I can write ma. So what is kinetic energy? Kinetic energy is equal to mas. In the place of force I wrote ma and displacement is as it is s. Therefore kinetic energy is equal to mas. We know the equation of motion. We studied there are three equations of motions. In that I am using a third equation of motion, v square minus u square is equal to 2as. When we use this equation, from this if you take out acceleration, then what we will get? Acceleration a is equal to v square minus u square by 2s. If I substitute this equation 2 in equation 1, then what we will get? We get the kinetic energy Ke is equal to m into v square minus 0 square by 2s into s, right? I substituted this v square minus 0 square by 2s in the place of acceleration a. Then we got mv square by 2 or half mv square. So this is the mathematical expression for kinetic energy. So what is the formula for kinetic energy? Half mv square, where m stands mass of that body. What is v? The velocity of the body, right? So the kinetic energy of the body is always equal to the half of the product of its mass and square of the velocity of the body, right? This is how we can derive expression for kinetic energy. From this equation we can say that kinetic energy depends on two things. What are they? Number one, kinetic energy is always directly proportional to the mass of the body, right? It is depending on mass. So if mass is increased, kinetic energy also increases, right? Larger the mass of the body, greater is its kinetic energy. And the second one is kinetic energy also depends on square of the velocity, right? Ke is proportional to v square. Higher the velocity of the body, greater is its kinetic energy, right? Now we will see what is the relation between kinetic energy and momentum. We already learned in force and laws of motion chapter momentum. Momentum is what? Momentum is the product of mass and velocity. The physical quantity which is the product of mass and velocity, we call it as momentum, right? Now we will take the body mass as m and it is moving with velocity v, then definitely the momentum of the body will become mv. P is equal to mv, right? And we got kinetic energy expression. Just now we derived, that is Ke is equal to half mv square. Now these two when we use, so when I take this equation 1 in equation 2, or if you multiply and divide the right hand side of equation 2 with m, we get k is equal to m square v square by 2m. What I did, I multiplied and divide the right hand side of the second equation with mass. Then I got m square v square by 2m. Why I did? Because I know momentum p is equal to mv. So I want to substitute mv place. I want to substitute momentum. So here mv whole square is there. Therefore, I can write in the place of mvp, then it becomes kinetic energy is equal to p square by 2m. This is the relation between kinetic energy and momentum. What is the relation between kinetic energy and momentum? Ke is equal to p square by 2m. Okay. Now we will see theorem about work and energy. We already discussed about work. Now we got kinetic energy. Now what is work energy theorem? So work energy theorem says that work done by any unbalanced force, definitely it will be equal to change in kinetic energy. So now this theorem we will try to discuss. So for that, consider a body of mass m moving with initial velocity u. And now this body, which is moving with initial velocity u in a particular direction, let us assume we applied force on it. How we applied force? In the direction of motion only we applied force. Why we applied force? So to change the velocity. So we are changing the velocity means we are changing the kinetic energy. We know whenever we apply force, it gets displacement. Let the displacement of the body is s. When I applied f amount of force, the body got displacement and it is s, right? And now after displacement s, let us assume its final velocity is v, right? Like this previous one, we discussed the same thing we are following. Initially, before applying force, body was having initial velocity u. In one particular direction, it was traveling. Now I applied force on it, f amount of force, because of which it got s displacement. After s displacement, let the final velocity of the body is v. Now in this, we say body got acceleration. Let the acceleration of the body is a, right? Now we can write it as, we know already third equation of motion, v square minus u square is equal to 2as. From this, what is a? A is equal to v square minus u square by 2s, right? And we know, so Newton's second law says force is the product of mass and acceleration, that is F is equal to ma. In the place of a, I am substituting the third equation of motion. Then force will become m into v square minus u square by 2s. Now we will try to calculate work. We know force is applied in the direction of motion. Body got displacement after applying force. Both force and displacement, as they are in same direction, we say positive work is done, and we will try to calculate that work done. So when we calculate the work done, we know work is the product of force into displacement, as it is positive work, right? And force is F, displacement is S. We know already force, right? And when we substitute force value, we will get W is equal to half mv square minus half mu square. Half mv square is what? This is the final kinetic energy. What is half mu square? It's the initial kinetic energy. So that means work is done, and that work done is equal to change in kinetic energy, right? Work done on a body, on a moving body, always equal to what? It is equal to change in the kinetic energy of that body, right? This itself is called as work energy theorem. So what is work energy theorem? Work energy theorem is work done is always equal to change in kinetic energy, right? So we will stop our class today here itself, and we will see in the next class about potential energy. We know mechanical energy is also available in the form of potential energy. So we are going to discuss potential energy in the next class. Thank you.